Hello and welcome to another one of our online lecture videos for differential equations. Today is a very special day. Today we're going to be taking a look at Euler's method. Now, Euler's method gives us a way that we can get a numerical approximation to a solution to an initial value problem. And here we'll talk about what Euler's method has us doing. And Euler's method says the endpoints given as ordered pairs, x sub 0, y sub 0, next would be x sub 1, y sub 1, next would be x sub 2, y sub 2, so on and so forth, until we get to the end, x sub n, comma, y sub n. And these endpoints of the line segments approximating the solution of an equation on the interval x goes from a to b are given by the following formulas where h is b minus a divided by n. And this expression here for h probably looks familiar from calculus. I prefer to actually think of this as the ever popular delta x. But calling it h is fine as well. It's going to be our step size is what we refer to it as. Now first let's talk about this column here with the x values. The very first x value, x sub 0, this is equal to some value that's given, so here we're calling it a since x goes from a to b. But then to build to the next x value, for example x sub 1, I would take the previous x value, x sub 0, and add to it this change in x, h, or the step size. So we'd say, well here, if I'm currently at x sub 0, to get to the next x value, I would take the current x value and add to it that change in the x direction. And that bumps me up to my new x value. And so on and so forth. So we have this recursive relationship where then next x sub 2 would be equal to x sub 1 plus h. X sub 3 then would be equal to x sub 2 plus h, so on and so forth until we get to the very last x value, x sub n, which is equal to the previous x value, x sub n minus 1 plus h. And we could even mention here that since x is going from a to b, this value for x sub n should be equal to that value b. Now the y values have a little bit more going on for them. Y sub 0 is some given value, and that would be given with an initial value. Then to find the next y value, so for example y sub 1, we would take that y value, y sub 0, and add to it, this is the differential equation f evaluated at x sub 0, y sub 0, so that's the previous x and y, and then multiplying that by h. And then so on and so forth. So y sub 2 is equal to y sub 1 plus the differential equation evaluated at x sub 1, y sub 1 times h, so on and so forth, until we get to our last value that we're looking for, y sub n, would be y sub n minus 1 plus the differential equation f evaluated at x sub n minus 1, y sub n minus 1 times h. And this would be for the initial value problem, where dy dx is equal to some function f, so here we're calling this function f, but that's our differential equation, with the initial condition y at a is equal to y sub 0. And I like to talk about where this comes from, but let me save that for the end of the video. We can go through our examples first, and then we can return back here to this first page and talk about what's sort of happening here. I can try to give some sufficient ideas to what's happening here. I think the easiest way to go through this, and Euler's method is very formulaic, we have these recursive formulas we're working with. The easiest way to do it, in my opinion, is to work with a table of values. So here we're going to start with the header for all of the columns. The first column is going to be for the x values. The next column, right alongside it, is going to be for the y values. Then we're going to have a third column, and it's going to be for y prime, or dy dx, which is our function f, a function of x and y. And then we're going to have a final column where we're going to take what we got for y prime, and we're going to multiply this by h. And we're going to fill this out row by row. In fact, we can actually fill out all of the x column first, and I like to do that because it gives me an idea as to how much work is involved. And then we should have that first y value. We go ahead and we work through, we get this y prime times h entry. We're then going to have to add it to this y value from the same row to get us that next y value. And we'll take a look at lots of examples so we'll get comfortable with Euler's method overall. but I really do think that the best way to go about it is to arrange information into a table. It just helps keep our workflow nice and neat and makes it a little bit more memorable as to the steps involved. For these examples, we're going to apply Euler's method twice. So we're going to do it once and then again with different step sizes. We're going to be getting an approximation for the solution on the interval from 0 to 1/2, so a small interval on x, subjectively, with step size h equals 0.25 and then with step size h equals 0.1. And we're going to compare these with the exact solutions. And here we have our first example, y prime is y plus 1, with initial value y at 0 equals 1. So let's build our table first. So this is going to be for step size, I'll put a note here, h equals 0.25, or that's 1/4. I'm going to build my column for x values. I'm going to need a column for y values. Here's where I'm going to put y prime, and I'm going to remind myself what that differential equation is. That's y plus 1. And then we're going to need a final column here for y prime times h. And here I'm going to remind myself over on this side as well that h is 0.25, or 1/4. Just so I don't forget, on my best behavior today. Now, I said I like to fill out the x column first. We're told that the interval that we're going to be looking at for both iterations of the same problem is the interval from 0 to 1/2. So x is going to start at 0. And then to get to the next x value, I want to add the step size. So 0 plus 1/4 gives me 1/4. And then I want to keep doing this. I want to add the step size again. 1/4 plus 1/4 gives me 1/2. And since I'm only going from 0 to 1/2 in the x direction, that's as far as that column would go. So then here I can go ahead and sort of build my designated rows, and I have an idea as to how my table looks in full. Now we want to start filling out the rest of the information. Let me do this in a bit of a different color so it stands out a bit. I'm given the very first y value with this initial value. It says y at 0 is equal to 1. This means when x is 0, y is equal to 1. So I can fill that in. So that's an ordered pair. X is 0, y is 1. Now what I do is I keep moving along this first row. I want to move into the next cell where here I'm going to evaluate y prime, and y prime is y plus 1. So we see it doesn't rely on x in this example. So then we get y prime is equal to the y value, which is 1. So I'm pulling the information from this row. So y plus 1 is going to be 1 plus 1, which gives me 2. And then I bring this into the next cell over where I take this answer that I just got for y prime, which was 2, and I multiply this by h. And here h is 1/4. So 2 times 1/4, or that's going to give me, reduces to 1/2. Now to get the next y value, and this is something we want to remember with our table, is I want to add this to the current y value to bring me to that next y value. So although I have this last value 1/2, that's not my new y value. I have to add it to this previous y value. So we'd say 1 plus 1/2, or think of that with common denominator, 2 over 2 plus 1 over 2. That's going to give me 3 over 2. If we go back to the formula, we can see that's what's supposed to be happening here. So what we do is we evaluate the differential equation, which we did, multiply it by the step size h, but then we have to add it to that previous y value to push us to the next y value. And now we have a new ordered pair. We're saying when x is 1/4, y is approximately 3/2, roughly. Now we go through this again. So now I go into the next cell. I want y prime is y plus 1. So here y prime is equal to, now I'm using the y value 3/2. And I'm going to add 1 to it. So think of this like 3/2 plus 2 over 2 is going to give me 5/2. And I want to bring this into the next cell where I have to multiply it by h. And h isn't changing. So I have 5/2 times h is still 1/4. And that's going to give me 5 over 8. Now I want to take this value to get my new y value, I have to add it to my current y value. So we'd say here I take this 5/8 that I just found, and I have to add it to 3/2, the value right up above, directly above it. And now get a common denominator here, so 5/8 plus 3/2, if I multiply by 4/4, gives me 12/8. And then here adding, that's going to give me 17/8. Or if I want to compare this at the end, I can get this as a decimal value. Well, a pretty exact one. 17/8 is going to give me 2.125. So either one of these would be okay. Let's say 17/8. And this is an approximation by Euler's method. What we're saying is when x is 1/2, y is approximately 2.125. Now, something that I always notice when doing the table method, or something that we can comment on, is that we have these extra 2 cells left over. I don't want to use those. The idea is I want to use Euler's method until I have a corresponding approximation for y when x is 1/2. We're told x is just going to go from 0 to 1/2. So right here, I'm done. If I were to fill out these other 2 cells to complete the row, that would be if I wanted to continue forward with more of Euler's method, if I wanted to move and talk about next x values and what their corresponding y's would be. So it sort of feels a little bit strange because I think we're very used to building a table and filling out all of the table, but I would only fill out these next 2 entries if I wanted to keep going with the process. So I always like to go to these 2 empty cells and I like to say, we got room for rent. Because I don't actually intend on filling those out. So we have our approximation with Euler's method. Now I want to go back and I want to do this again. We said we're going to take a look at the same example twice, a second time with step size h is 0.1. And then we're going to compare this with the exact solution. So I have to build another table. Things just keep getting better. We got another table. And it's going to have the same headers. I'm going to have my x value, then my y value. Then I'm going to want y prime, which is y plus 1 still. And then I'm going to want y prime times h. I'm going to put a little note for myself that h is 0.1. We're changing that. And now I want to go and fill out the column for the x values. So x is still starting at 0 and going to 1/2, but now it's moving with step size 0.1, or 1/10. So here we'd say starting at 0, and then if I add h to this, 0 plus 0.1 gives me 0.1. And then I want to add h again, 0.1 plus 0.1 gives me 0.2. Then I want to add h again, 0.2 plus 0.1 gives me 0.3. I want to add h again, gives me 0.4. And then we add h one more time, brings us to 1/2 or 0.5. So now I have an idea as to how my table should look when I'm filling it out. Draw these horizontal lines in for the rows. You know what we're doing, building our table. And we go through the same process, just there's going to be more of it. So now I see I got more work until I get to the end. But I still have that same initial value. The initial value was when x is 0, y is 1. So that should start this all off. So let me switch to a different color. X is 0, y is 1. And I plug into my differential equation, plugging into really the right-hand side of it, but we'd say y prime is equal to y plus 1, which is 1 plus 1, which is 2. And I take that value into the next cell, I multiply by h. So 2 times 0.1, it's going to give me 0.2. Now I want to take this value and add it to the current y value. So I take that 0.2 that I just got and I have to add it to 1, and that's going to give me 1.2. So here I get 1.2 to start. Now I continue on with the same process, so it gets very sort of repetitive, right, with our formula. So I want to plug into y prime next. So here y prime is y plus 1, which is going to be 1.2 plus 1, which gives me 2.2. And I bring that value into the next cell, 2.2. I got to multiply it by h, which is 0.1, or this gives me 0.22. Just moving the decimal over, right? Now I take this value and I add it to that current y value to bump me up to the next y value. So we get 0.22 plus 1.2, and that's going to give me 1.42. And then again, right, so we keep doing this. So now I go to my differential equation. Y prime is y plus 1, so that's 1.42 plus 1 gives me 2.42. I go into the next cell. I take the 2.42, I multiply it by h, which is 0.1. This gives me 0.242. And now I have to add this to my current y value. So 1.42 plus this 0.242, and that's going to give me 1.662. And then I go finish this next row, right? So y prime is y plus 1, so 1.662 plus 1 gives me 2.662. And then I want to go into the next cell. I want to multiply this by h. Let me know in the online discussion board if you're having fun yet with Euler's method. It's not so bad. That's something I can definitely say about it. Multiply by h, so that's going to give me 0.2662, and we're almost done. So don't lose sight of the goal. We're almost done. We got to do this one more time, and then we're going to be done. So I have to take what I just got for y prime times h, and I have to add it to my y value to get that next y value. So 1.662 plus 0.2662, and this is going to give me 1.9282. One more go of it. Are you ready? Get pumped. Let's take a look at what we get. Plug into y prime. So y prime is going to be y plus 1. 1.9282 plus 1 gives us 2.9282. And then I take this value, 2.9282, and I multiply it by h, which is 0.1, gives me 0.29282. And now, to find this final y value, I add this last value at the end of this almost last row, and I add it to the y value at the beginning. So here, well, at the beginning of that row. So 1.9282, I want to add to this the 0.29282, and then this is going to give me 2.22102. Remember, we don't intend on filling out these extra cells, so it's okay if I sort of ran into them at the very end here. These we'd say are for rent. I don't need them. And that here is my answer. So now what we're saying is when x is 1/2, that y is approximately 2.22102. And so now I can compare this with what I got previously. Before we said y is about 2.125. Now we're getting something that's about 2.22102. Which one do you think is better? Well, hopefully this recent one that has more work involved is better, or else why are we doing it, right? But what's nice is with these examples, we can actually check. Now you're not always able to check, so a good question is, hey, if we're checking these against the exact solution, why are we using Euler's method? And there's a couple sort of answers that I would have to a question like that, but let's write this down first. Y prime is y plus 1. So we'll go here, y prime is equal to y plus 1. With initial value, y is 0 equals 1. Now, unfortunately, and this is sad to sort of say at the beginning of the semester sort of, is that we can't solve every differential equation. So an initial value problem, it's nice to have a backup, right? Just like I deal with Riemann sums in calculus, we want some numerical method that we can fall back on if we're not able to really have any success with calculus or something like that. Also, what's nice about this method is that I don't have to know anything about solving differential equations to get these approximations. All that I've done throughout the work was, and we obviously have to understand what the formula is doing enough to plug in and evaluate these pieces, but at the end of the day, it's just pre-calculus stuff. I'm just evaluating functions, multiplying, a lot of arithmetic. I don't need to know anything about calculus really, just pre-calculus topics in order to go through this formula, these recursive relationships. But of course, I do think these approximation methods are best in the classroom when we can take a look at how close they are. So a good question is always, well, how good are they? If I can't actually get the true solution, I won't be able to judge them. So what's nice is that with this example, I can actually find the true solution. So I could solve this in a couple of different ways. We could use integration factor method, or we could treat it as separable. Let's treat this as separable. So y prime is dy dx is equal to y plus 1. And I can multiply the dx over, so dy is equal to y plus 1 times dx. And I can divide the y plus 1 to the other side now. So 1 over y plus 1 dy is equal to dx. Now from here, we would want to integrate both sides. And integrating on the left with a substitution method, it's a very small substitution. So I'll just jump to the antiderivative. That's natural log of y plus 1 equals, we integrate 1 with respect to x, gives us x, and then plus a constant c. And then solving for y, I want to raise both sides as exponents to base e, so e to the natural log of y plus 1 equals e to the x plus c. Here the inverse functions undo one another, so on the left I just get y plus 1. On the right, I can break this up into e to the x times e to the c. But here e to the c is just some constant, so let me call that c and write it in front. We'll say c times e to the x. And then to solve for y, I just have to subtract 1 over. So we can build the general solution first. Y is c times e to the x minus 1. And now I can work with my initial value. So let me actually do that down here, since I'm already down here on the PDF. Y at 0 is equal to c times e to the 0 minus 1. And e to the 0 is just 1, so we get c minus 1. And we also said earlier that y at 0 is equal to 1. So c minus 1 is equal to 1. So then if I add 1, that means c is equal to 2. So now we get a particular solution. Y is equal to 2 times e to the x minus 1. And since I have the particular solution, I can now tell you what y is going to be exactly when x is 1/2. So I can go up here and say, well, when x is equal to 1/2, y is equal to 2 times e to the 1/2 power minus 1. So just plugging 1/2 in here for x, 2e to the 1/2 minus 1. And this gives me, for the y value, I would want to evaluate this with some calculator, get some decimal value. This should give me 2.29744, and this is obviously a rounded value since I stopped writing the decimal at some point. I'm not going to use the little squigglies to show this is approximately it, because I want to remember that this is the exact. It's an approximation of the exact value, if that's not too funny to say it that way. So this is what the true value should be in solving the differential equation and finding what y at 1/2 is. And now we can go back and judge what we got. So we should have been getting 2.29744 about, right? That's what we should have been getting. And here I got 2.22102, so this is very good, I think. And earlier, with almost pretty much next to no work, I was able to get 2.125. Is it close enough? That's sort of subjective, right? So I'd look at this and I'd say, it's reasonably good considering the amount of work I had to go through was very small. So I'd say this is a good approximation for almost no work, very quick. And this was an even better approximation, just decreasing that step size to 0.1, increasing the amount of work we're doing. And here's that exact value. It's good that they're reasonably close. If this was completely different than what I had for either approximation, then that would be sort of grounds to maybe go back over and check the work and make sure that I didn't make any mistake, because hopefully Euler's method is some reliable approximation in some measures. Now here we have some pictures of what's happening. These aren't the greatest visual representations. When I'm doing Euler's method, I'm building ordered pairs. So we get when x is 0, y is 1. When x is 0.1, y is 1.2. Our approximation of it is, at least. When x is 0.2, y is 1.42, so on and so forth. So really, this should be approximating with line segments. So here that approximation, which is in blue, should have almost sort of this point-by-point line segment connecting aesthetic to it. And here it looks sort of like that, but maybe a bit smoother looking, sort of zoomed out. And we're comparing this against the exact solution, which I do have graphed here in the orangish color. And we can see this first visual representation is for that step size h is 0.25, or 1/4. And it's pretty good. We can see that starting off it's really great, but then as time goes on, as we start going through the iterations, we notice that these curves are growing apart, so that our approximation in blue isn't quite keeping up with the exact value in the orangish color. So we'd say, well, okay, so it's good, it's not great, and we can see that as time goes on, it starts to get worse progressively. Here I have same exact visual representation, but now for h equals 0.1. And here we can see that the approximation, sort of as a curve here, is keeping up with the exact solution a lot better. So it is still, so at the beginning it starts off good and it stays good for a while, but then a little bit better, but as time goes on, as we move further out in the x direction, it does start to separate a bit from what our exact solution should be. So here we get a nice visualization, so we can get an idea, sort of visually, graphically, how well Euler's method is working in this example. Hey, let's do another one. So let's take a look at, and this is going to be the same situation where we're taking a look at x from 0 to 1/2. We're going to take a look at step size with 1/4 and step size with 0.1. If you want to use decimals, that's fine. So we'll take a look at doing this twice over. And here we have new differential equation. We got initial value as well. So we have y prime equals y minus x minus 1. Let's build our table. So x is going to be our first column. Then we're going to have y. Then we're going to have y prime, which I like to remind myself is y minus x minus 1 now for this example. And then a last column for y prime times h, and we're going to start off with a step size h is 0.25. Now what I can do to start is I can go ahead and begin just by filling out the entire x column. So we'd say x is going to start at 0, then if I add h, 0 plus 1/4 brings me to 1/4. If I add h again, 1/4 plus 1/4 brings me to 1/2. And then I can create my rows. And we can start filling in the table. Now the initial value is given. It says when x is 0, y is 1. So 0, 1 is that first ordered pair. Go into the differential equation. Now this does rely on both y and x, so I should be plugging in for both. So y prime is equal to y, which is 1, minus x, which is 0, minus 1. You'd say, okay, well 1 minus 0 is 1, 1 minus 1 gives me 0, so this is 0. And if I go into that next cell, we get 0 for y prime times h, which is 1/4. 0 times 1/4 gives me 0. Now this will sometimes happen with Euler's method, and what I'm going to notice is that my startup is a bit slow. There's sort of a bit of a stutter here. since when I take this value that I just got, 0, and add it to my current y value, it bumps me up to the next y value, but that y value is still 1. And that's okay, right? That can happen. That just means that we want to go through maybe another iteration and see if it starts to move in the y direction as well. But this shouldn't be anything that's a cause for alarm. This does happen with some examples. All right, well, let's go ahead and go through it again. Let's plug into y prime now. And here we're going to use 1 for y. So we're looking into this row that we're working in. So that's 1 minus x, which is 1/4 currently. So 1/4 for x, and then minus 1. And here we could say, okay, well, 1 minus 1 cancels. So I'm just really left with this negative 1/4 for y prime. And I can bring it into this next cell, negative 1/4, and I can multiply it by h, which is 1/4. And so this gives me negative 1/16. Now I want to take this value and I want to add it to my current y value. So I want negative 1/16 plus 1. And then here I'll get a common denominator. Negative 1/16 plus 1 is 16/16. So this gives me 15/16. Or if I'd like to sort of compare this, I think decimal numbers are going to be the nicest way to do that. We'd say here this gives me a decimal value of 0.9375. So 15/16 by hand is easiest for me, but as a decimal value, 0.9375. And remember, if you can cover utilities first and last month's rent and the pet deposit as well, we got some spaces for you here. You can buy out some spaces in my table. You can put your advertising here. If you've got a product you're trying to sell, I got space for you. So there's Euler's method with step size 0.25 or 1/4. But now we get to do it again, see if we can improve on what we've done with a step size of 0.1. So x, and then we got y. We got y prime. What was that? Y minus x minus 1? Yeah, y minus x minus 1 was my differential equation. And then y prime times h, and here we're going to be using h as 0.1. And let's fill out the x column. So 0, 0 plus h gives me 0.1. If I add h again, I get 0.2. If I add h again, I get 0.3. If I add h again, I get 0.4. And then if I add h one more time, I get 0.5, which is where we're going to stop because we're only going from 0 to 1/2 in the x direction. So that's as far as I'm going to have to go. We have that same initial value from before, which was y at 0 equals 1. And I get that to fill in my very first entry. So here, when x is 0, y is 1. And then we plug into the differential equation now. So we get y prime is equal to y, which is 1, minus x is 0, minus 1. So this gives me that y prime equals 0 that we saw kind of earlier. If I multiply this by h, 0 times 0.1 gives me 0. And I see I have sort of a bit of a slow startup to my table for moving in the y direction, because when I take this 0 and add it to 1, it's going to keep me at 1 for now. But we expect it'll start moving soon, right? You got to get that cup of coffee in the morning. Looks like y hasn't had that first cup of the day yet. Once it does, it's going to start moving for us. So let's go ahead and take a look at this next row. Plugging into y prime, we get y, which is still 1, minus x, which is 0.1, minus 1. And here 1 minus 1 is going to cancel. We get negative 0.1 for y prime. And we go into the next cell where we want to multiply by h. So this is negative 0.1 times 0.1 is going to move the decimal, so we get negative 0.01. And then now I want to add this to my y value, so negative 0.01 plus 1, that's going to give me 0.99. And now into the differential equation again. So we keep going, a lot of the same process all over again, but what we're inputting for x and y keeps changing. So here y prime is equal to, it's going to be y, which is 0.99, minus x, which is minus 0.2 minus 1. And I can go through and calculate this. So this is going to give me y prime equals negative 0.21. And then I want to bring this into the next cell, negative 0.21, multiply by h, which is 0.1. So this gives me negative 0.021. Negative 0.021. And I want to take that value and add it to the 0.99 to get that next y value. So negative 0.021 plus 0.99, and this is going to give me 0.969. A little bit left to go. The end is sort of in sight. So I'm plugging into the differential equation again. Y prime is equal to y minus x minus 1. So for y, we're using 0.969. Minus x is 0.3 minus 1. So then here for y prime, we're going to get negative 0.331. And then I want to multiply this by h in the next cell. So negative 0.331 times 0.1 is going to give me negative 0.0331. And I want to take this and add it to my current y value. So negative 0.0331 plus 0.969 is going to give me 0.9359. One more go of it. Are you ready? Let's jump right in. So y prime is y, which is 0.9359, minus x, which is minus 0.4, minus 1. If I go ahead and evaluate this here for y prime, we're going to get negative 0.4641. And multiplying this by h, which is 0.1, we know what it's going to do. It's just going to move that decimal over one spot, so negative 0.04641. And now I can get my final answer. I just want to add this value that I got from y prime times h to this current y value to get to my next y value. So here we have 0.9359 plus this negative 0.04641, and that this should give me 0.88949. And this is where we would stop. Remember, these extra cells here, I have no intention of filling them out. So, space for rent. But what we're saying is, when x is 1/2, y is approximately 0.88949. And what did we get before? I didn't write my little statement here, so I should do that. When x is 1/2, y is approximately 0.9375. Are these the closest numbers in the world? 0.9375 and 0.88949? No, of course, but reasonably close to one another, I'd say. So now a good question to ask is, well, what's the exact value? How good are either of these approximations compared to the differential equation that we're looking at? Well, let's see. So we had y prime is equal to y minus x minus 1 with initial value y at 0 equals 1. Now for this, I'd want to work with the integration factor method. So I can subtract y over, so get y prime minus y equals negative x minus 1. And we'd say, what is the coefficient on y? Well, the coefficient on y is negative 1, and I want to integrate that. And here we're going to integrate with respect to x. This gives us -1 times x, or negative x. So then we build our integration factor from this as e to the power of minus x. Now I want to multiply this e to the minus x to both sides of the differential equation. So I get e to the minus x times y prime minus y in parentheses equals e to the minus x times negative x minus 1 in parentheses. And then here on the left, I can go ahead and distribute in. We'll say e to the minus x times y prime minus e to the minus x times y equals e to the minus x times, in parentheses, negative x minus 1. And this left-hand side, very true to our integration factor method, I should be able to condense this and write it as the derivative of a product. It should be the derivative with respect to x of my integration factor, which is e to the minus x, times y. And I can check that through product rule. So we'd say here, I would start by rewriting e to the minus x, there it is, times the derivative of y, which is y prime, there it is. Then I would add to this, now I would rewrite y, there it is, times the derivative of e to the minus x, which is e to the minus x times -1. So all of it's there, it's true. I'm not lying to you, I promise. It's the integration factor method, still working out for us. And then on this other side, I just have whatever I have, that's e to the minus x times negative x minus 1 in parentheses. Now, something that might not be a bad idea to do here, I want to integrate both sides, is to think about how we're going to integrate on this right-hand side. Because remember, for the left-hand side, we don't really intend to integrate. We would say the antiderivative, let me get notation here, with respect to x, of the derivative with respect to x is just going to undo one another over on the left-hand side. So this should just leave me with e to the power of minus x times y equals, but I do have to do the integration over on the right. I'm very happy to say that the integration on the right-hand side is going to require integration by parts. So I'm going to pick my choices for u and for dv. Since I have an exponential function, that should be my choice for dv, this e to the minus x dx, which means the power type function, minus x minus 1, is my choice for u. Now differentiating u gives me du equals -1 times dx. And integrating both sides of my dv statement, I get v equals e to the minus x divided by -1, or that's minus e to the minus x. And then I want to plug into my formula's right-hand side. That's the integral of u times dv, which is what I'm starting with, is equal to u times v minus the integral of v times du. Now u times v, if I just multiply these together, notice I have this minus sign that I can distribute through. So this is going to become positive x plus 1 times e to the minus x. And then I have minus the integral of v, which is negative e to the negative x times -1 dx. So v times du. So here I have x plus 1 times e to the minus x. Here the minus 1 and the subtraction symbol can resolve, so I'm left with plus the integral of this negative e to the minus x dx. And my u times v just keeps carrying along, so x plus 1 times e to the minus x. Here I integrate minus e to the minus x, the minus sign comes along. Integrating e to the minus x, thinking of it as a substitution, gives me e to the minus x divided by -1, and then plus my constant c. So then here we have the antiderivative. I just want to clean up this double minus sign. So we have x plus 1 times e to the power of minus x, minus a negative is plus e to the minus x, and then plus c. I like integration by parts. I hope you do too, but whether or not you like it or not, we did just do it. So I win. Just kidding. I'm just trying to have a good time. So here, if I go ahead and try to solve for y, that means I want to divide both sides by e to the minus x. So y is equal to x plus 1 e to the minus x plus e to the minus x plus c all divided by e to the minus x. Now think about breaking this up into 3 separate fractions and simplifying. This first fraction, e to the minus x over e to the minus x, will cancel, so I'm just left with x plus 1, plus the second fraction, e to the minus x over e to the minus x, will cancel, giving me 1. But don't forget about this last term here, which is c divided by e to the minus x. And I can't just call that a constant. It is a function of x now, since I'm dividing it by a function of x. But I can still clean this up. So here we get y is equal to, I have x plus 1, which is x plus 2, plus c divided by e to the negative x. I can write this as a product, c times e to the x. And this is my general solution. Now from here we had that initial value, that y at 0 is equal to 1. So I can go ahead and work with that to solve for my constant c. If I plug 0 in for x, I get y at 0 is 0 plus 2 plus c times e to the 0. 0 plus 2 is just 2. E to the 0 is 1, so c times 1 is c. So 2 plus c equals 1. And if I subtract 2 on each side, I get c equals 1 minus 2 gives me negative 1. And now that I know what c is, I can go ahead and write down what the, well, let me use this space up here so I can compare it a bit better. So I have y is equal to x plus 2. We'll start with that. And then plus c times e to the x, but c is minus 1. So minus e to the x is really what we mean there. Minus e to the x. And now I can find what y at 1/2 is. That's 1/2 plus 2 minus e to the 1/2. And if I go ahead and evaluate this, this should give me 0.8512,787. And now I can compare it against these approximate values that I got from Euler's method. So 0.88949, it's not amazing, but it's pretty close to 0.8512787. For even less work, I got 0.9375. I'm not saying we should put our foot down at any point, but this doesn't really seem to be the best approximation, but it is certainly better than guessing or just not knowing. So 0.9375, although it's not incredibly close to 0.8512787, it's still, you know, not miles away, I would say. So we can get an idea as to how well Euler's method is working. I got this picture here. So this, I just went through and depicted for h equals 0.1, just so we can get an idea as to how well it is. We see this one's not doing quite as nice as that first example's visualization. I have my approximation in blue and my exact solution in the orangish color. You see it starts off really good, but then very quickly it starts to cut away from it. So we have some visual reassurance that our approximations, maybe not going to be as good as we'd like them to be for this example, but they're still certainly doing the best they can. Leave them alone. They're doing the best they can. We'll take a look at one last example. Same sort of set of rules apply. For this one, let's go through the step size h equals 0.25 on our own together, and then I want you to look at h equals 0.1 on your own and let me know on the discussion board what you're getting. We will also take a look at the exact value together as well. So x, 0, and then 1/4 or 0.25. We add again, add h, brings us to 0.5. Going to need a column for y. Then for y prime, which is given this negative 3x squared y. And then here we'll have our final column for y prime times h, where h is 0.25, or 1/4. We're given the initial value y at 0 equals 3. So when x is 0, y is 3. I plug into the differential equation, so y prime is negative 3 times 0 squared times y, which is 3, which, since I have 0 as a factor, that's going to give me 0. And then y prime times h, that's 0 times 0.25, is going to give me 0. So we have another one of these, I like to call them the slow startups for moving in the y direction. When I add 0 to 3, my y value stays at 3 for this first iteration. But probably not going to stay that way. Now when I go and plug into y prime, I'm plugging in 0.25 for x, I'm plugging in 3 for y. I get y prime is negative 3 times x squared, which is 0.25 squared, times y, which is 3. And let's sort of a bit of real talk right now. We're not allowed any calculators for the exams of the course. However, there are maybe some examples in the homework where you might want or perhaps need to use a scientific calculator to help out. If we go back to any of those previous examples, although you could do the decimal arithmetic, you probably don't want to for the smaller step size of h is 0.1. And certainly comparing the exact value, getting some decimal approximation for things like e to the 1/2, that's not really something that I would expect you to know. And if you know it, then, I don't know, that's sort of a bit incredible. So I'm not really anticipating that. So for something like this, I think it's perfectly normal as a human reaction to think, well, hey, am I supposed to be doing this by hand? Can I use a calculator to help? So I want you to just keep in mind that for the exams, no calculators. We can certainly see and perform Euler's method without using a calculator. However, examples like the one we're looking at right now don't really seem to be fair or reasonable to do that necessarily. So you might want to find like a scientific calculator, like this one I have here. And again, just for the homework sometimes, or the classwork sometimes, this is a great example, this section, when the sometimes kind of happens. And you would go here to the calculator, you go bleep, bloop, bleep, blap, bleep, bleep, bloop, bloop. It's like a little robot friend, boop, beep, 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 plug in, and it's going to tell me, when I go ahead and do that, that what I'm getting for y prime here, that y prime should be negative 0.5625. And then I want to take this value, this negative 0.5625, and I want to multiply it by the step size, 0.25. And again, that calculator, bleep, bloop, bleep, 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 little robot friend helping me, tells me that that should be negative 0.140625. And then we use that same calculator friend to add it to our current y value. So 3 plus negative 0.140625 is going to give us 2.85938, sort of an approximate value here. So what we're saying is, when x is 1/2, y is approximately 2.85938. And that's Euler's method with step size of 0.25. Now next, we would use this sort of space here to take a look at step size h is 0.1. Now, these examples, they're maybe not the thing that I find the most joy in all of differential equations, but they're very important to our curriculum, and I think that they can be very enjoyable when we're comfortable with the method. So a big part of it is you being comfortable with Euler's method and that you can do it and work through it yourselves. So I would say this is probably one of those examples where you're going to need your robot friend, the calculator, but build the table, find this approximation. Let me know on the class discussion board what you got for your approximation, but I'm going to leave this for you to do because I think that it's a disservice if I just do all of it and never prompt you to take a look at it on your own. So I would say right now, pause the video, do this approximation, It's going to help a lot more than you'd think. One problem is going to help a lot right in the pith and marrow of our lecture, because that means that you are getting that practice, or you are consolidating what we're talking about right now. But let's go down here to this extra space that I have, and let's actually solve the differential equation and see what the exact value is. So y prime is negative 3x squared y. And y is 0 equals 3. This is great for the separation technique. So I would rewrite y prime as dy dx is negative 3x squared times y. I would multiply the dx over and divide the y over. So 1 over y dy equals negative 3x squared dx. If we integrate both sides from here, on the left we get natural log of y equals, if we integrate negative 3x squared, we get negative 3x cubed over 3, which is negative x cubed, and then plus our constant c. Solving for y, we want to raise both sides as exponents to base e. And e to the natural log of y power gives me y. Here I can split this into e to the negative x cubed times e to the c, so I get a product now. But then I can go ahead and think of this e to the power of c as just some unknown constant. So y is equal to c times e to the negative x cubed. And then we know y at 0 is equal to 3 is our initial value. If I plug 0 in for x, I get c times e to the negative 0 cubed power, which 0 cubed is 0, negative 0 is 0, e to the 0 is 1, so I get c times 1, which is c, and that this should be equal to 3. So we're able to get our particular solution now, that y is equal to 3 times e to the negative x cubed. Now if I want to know what y at 1/2 is, well, I can go ahead and plug it in. So that's 3 times e to the negative 1/2 cubed. And this is something that we're going to want a calculator to help with, certainly. The calculator is going to tell me that this gives a value of 2.64749. Now, last I checked, you were in charge of doing that approximation for h equals 0.1. So I want to know from you, did that one work out pretty close to this value? Hopefully it did. But I did with you, we did together, h is 0.25, so 2.64749, that's pretty close to 2.85938. Is it perfect? No. Do I expect it to be perfect? No. Euler's method is not a perfect approximation. It's an approximate approximation. And there's actually even other methods that are stronger than Euler's method. But we're not going to talk about those this semester. But so we see here, we get this approximation reasonably close. I do have a picture here somewhere. This is the picture for the one you were supposed to do at h is 0.1 for the step size. We see this one is also, I don't know if I would say underwhelming. That's not really nice to say. But I can certainly see that the approximation, although it starts off with good intention, has a bit of trouble keeping up with the exact solution perfectly. So of course, this is an approximation method. That is it for the section. Let me put the homework in the homework jar. Please take a look at the homework on our online homework platform. But let's just spend a little bit of time quickly